Clinics until and including the day of the exam. So we're still carrying on with daily clinics. Redemptions, even after the exam, like in Sem 1, for those that did this in Sem 1 as well. We'll still be doing redemptions on those ones. We do a quiz, the final quiz is in week 13, but we'll still take redemptions after that. So that's fine, you can still do redemption on everything. B1's due this Friday. Student feedback on courses, just to give you an idea, the email's been sent out this week. We get given that sort of stuff. So there's a radar plot of Sem 1's feedback. And that was saying things like, cancel. In 2016 compared to 2015, I went down in all these categories, up in those ones, down in them, but things were pretty good. So it goes round and tells us whether they'll look at things where we're failing a bit, not giving enough feedback and all that. So if you can do your course assessments, it really helps us out, whether you love it or hate it. The numbers are taken very much notice of. Just heard Ruth explain something about probability. Were you saying that it's good? Probability. Probability can go two ways. One, I think it's easier than most of the content, but as Dami was saying the other day, it can have language issues. English is a second language. Even us that just don't do English very well, probability can have issues. I think there'll be minimal ones with us, okay? This isn't too wordy. Next week, probability is a bit tougher. To anyone here or listening on Echo, next week's lecture is like logs in the way that if you've done the lecture, oh, okay, I get it. If you haven't done the lecture, there's no marks in it. Okay, so next week's content is pretty much either you either know it and you go well, or you don't and you don't get marks. And the whole last question of the paper, the final paper, is on, you know, last week or next week's lecture. So we've got a third of the lecture is on weeks 1 to 5, or weeks 1 to 6, sorry, and then it's just all of this stuff. So most of the lecture is these last 5 weeks we're doing, B1, 2, 3, 4, 5. And a lot of people throw away B5. Well, it's so close to the end, don't worry about that lecture. Please don't, it's just got too many marks in it to throw away. And they're not hard, you just got to have seen it before, okay? As for today's probability, well, you definitely will have seen this one before, okay? That was where we left off last week. We were talking about stats and those percentages, and hopefully we've got that for our resource sheets, maybe in the one with all the splits in it. And we said, okay, a certain percent of the data falls here. So stats analyse what happened in an experiment and so on. Probability overlaps with stats, and probability is when we say, look, you've got this percent of it happening. Okay, you have 68% of your result lying between here and here. So probability and stats do go hand in hand, but probability tells us expectations. Just a little intro, why would we bother coming up with probability? It was done for gambling, just to work out the odds of winning, to try and make more money through gambling, mostly cards and dice. Today, it's still, well, in gambling, it's still exactly it. You've got to look at your odds. Life insurance as well, if the amount they charge you, they ask you all these questions, smoking, family, health and all of that, well, they're trying to work out the probability of how long you'll live and how much money they're going to have to give you. Car property insurance, they give you give the postcode. They've got statistics on what happens in that postcode, and they look at the probability of your car getting nicked, so on. Share trading, medical considerations, you know, you've got a 5% chance of this happening, you've got a 95% chance of this happening. These are all sorts of considerations. We definitely do probability all the time. We take our risk when we go swimming in the ocean. We go, look, it's low probability I'm going to get done by a shark. It's possible, but it's low probability. So we're always doing this sort of thing in real life. And one of the main things we've got to go at first is the idea of randomness. That a lot of things I can't give you the probability of. If I did stick all these names into a hat and mixed it round and put out a name, say there were 80 of us here, it would be a 1 in 80 chance it's your name. Unless, of course, the papers were different bits of different sizes, different textures, unless there was some bias going on. But pure randomness is when everything's got the exact same chance of getting pulled out. All names are written on the same size bit of paper. It's well mixed. I haven't dodged it. That's randomness. So something like this: Adam, Ben, Chris and Dan put their names in a bag and one name is drawn out at random. The probability that the name drawn will be Adam's, he's got 1 chance out of 4 possible chances, so it's a dead set 1 in 4 chance, probability of 1/4. If there's a bit of a twist to that question, now I've got 5 people. Eli, Dean, Fiona, Greg and Harry run a 100-metre race. What's the probability that Eli or Dean wins? Now Sheldon's looking, because there are 2 potential twists. There's one main one that we're going for. And the gut instinct here could well be, well, that Eli or Dean, that's 2 people out of 5 people, so isn't it 2 out of 5? Why is A wrong? Well, it's 1 out of 5 for Eli, it's 1 out of 5 for Dean, if you want to think of it as a random experiment. There's something overall, there's an issue with my question. What if I told you that Eli was dead? You stand by the odds that Eli's got a 1 in 5 chance of winning? Okay, it's a harsh example. Do you really... I could have gone light on that. Okay, Eli's got a bad foot, but he's going to die from it. Would you say this is random? Does everyone have the same chance of winning the race? Who knows? I can't answer that question. 5 names in a hat. What's the chance of Eli or Dean getting pulled out? 2 in 5. No problem. But be careful of the questions. It just isn't random. Okay? I don't know anything about these people. I don't know if they're equal ability. It's like I've got 2 chances when I tee off. I don't play golf. I hate it. But someone that likes golf has 2 things that could happen when they tee off. They could get it in the hole, or they could miss the hole. So they've got a 1 in 2 chance of getting it in the hole? No way. Okay, it's not a random thing. It's not 50-50 chance in or out. Okay? So that's just the initial thing, just to say. Sometimes just analyse. Is this random? Numbers in a hat. Is this not random? Is there something else going on? So we've got a bit of terminology. Hopefully nothing too bad. Experiment, we think lab coats and so on. Experiment is just us tossing a coin. It's an experiment, rolling a die, whatever. That's another thing I'll say. I don't know if that's been said before. We say dice. Dice is plural. Die is a singular die. Okay? I've got 1 die, 2 dice. So don't get put off by the term die. It's just a singular of dice. So experiment is anything, yeah, tossing coins, whatever situation we're describing. Probability is the measure of likelihood of some event occurring. So the likelihood that I'll roll a 5. Whatever it is I'm after, I just want to work out a probability. It doesn't matter if you give it in percent, fraction, or decimal, okay? They're exactly the same. Hopefully first SEM or our background knowledge coming into this said, I can convert, they're all equal, so probability doesn't have a set form it's got to be. Any of them are good. An outcome of an experiment is just what happens, okay? What did you roll? That's the outcome. So rolling a die, the outcome might be just a 3. Fair enough. Sample space, okay, that's a bit more different maybe, but a sample space is just listing what could possibly happen. In the experiment of rolling a die, the sample space is 1, 2, 3, 4, 5, 6. I've got the curly brackets there, those parentheses things. We don't have to go there. That's sort of set notation. If you go further with this sort of stuff, they care about the way you write it. We don't care. We just want you to know the sample space is a list of everything that could happen. If I'm tossing a coin, my sample space is head, tail. That's it. An event, when we talk about what's the probability of an event happening, it's just the statement we make up. What's the probability of rolling a 3? What's the probability of maybe getting an even number? So my sample space there of the outcome that I desired is a 2, a 4, or a 6, an even number. So an event is just what you're asking the question about. Mutually exclusive events cannot occur at the same time. Like a 3 and a 6, they're mutually exclusive. You could ask what's the probability of getting a 3, what's the probability of getting a 6, but 3 and a 6 just can't happen. So mutually exclusive events just can't occur at the same time. I could do what's the chance of throwing a coin and a die and getting a head and a 3. They're not mutually exclusive, they can both happen. Head and a tail can't happen. Successive events just means one after the other. I do something, then I do something else. So maybe talking about getting a 3 and then a 4. Notice successive, the order matters. This is where a bit of our English comes into it. Just look for the word then. It's a different question. What's the probability of rolling 2 dice and getting a 3 and a 4 versus what's the probability of rolling 2 dice and getting a 3, then a 4? In one of them it says, I want a 3 on the first and 4 on the second. If I just said 3 and 4, I don't care which one's 3 and which one's 4. I just want a 3 on one, 4 on the other, or the other way around. So then implies there's an order. We've got a lot of examples coming up today. Independent is where two things are happening. You've got successive events. They're independent if the first event has no effect on the second event. Like, what have I got here? If I rolled a 3 on the first roll, does that affect my outcomes for the second roll? No. If I have a die and a coin, if I toss or let's just go two coins. It's actually a bit of a concept problem. If I toss and I get a head, does that make it more likely I'm going to get a tail with the other one? Still exactly the same. They're independent. You might say it's less likely overall to get 2 heads, but no. If I've already tossed a head, it's still a 50-50 chance here. They're totally independent. So in that case, what are dependent events or non-independent events? Say I had 3 red marbles and 3 green marbles. There's 2 questions I might come up with. One is, I take a marble out and then I take another. Or I could say I take a marble out, look at it, replace it, and then take another. The second thing I said, if I take it out and then put it back in, they're independent events. But just say I take a red one out and I don't replace it, the odds of getting a red then change. The odds of getting a red out of the first one, the probability of getting a red was 3 out of 6, same as a half. But if I did that and didn't replace it, my chance of getting a red second time round is only 2 out of 5. So the outcome of the first event did affect the second one. But if I'd replaced it after looking at it, they'd be independent. We don't have to go into all the terminology too much. The questions will be mostly just be able to work out in common sense. It'll say with replacement or without replacement, and a few little sketches like that, and it won't be a big mathy thing. It's just making sure you're reading the question properly. So simple probability. Please don't think you need this formula. Okay, this is not a formula to memorize or to bother putting on a resource sheet. It's just an explanation of what we probably already naturally do. To say the probability of an event happening is equal to the number of ways it can happen. In other words, the number of events. Maybe if I wanted to roll an even number, I'm saying how many events are there? Well, I want a 2, 4, or a 6 because die only goes from 1 to 6. And the sample space here is 1, 2, 3, 4, 5, 6. So all this formula is saying is, oh, there we go. Yes, yeah, even number when a die is tossed once. I've got 3 events that could happen to satisfy my question. There's total 6 outcomes that could happen. So my probability is just 3 on 6. And there's nothing wrong with an answer of 3 on 6. These fractions don't have to be simplified. 3 on 6 and 1 on 2, they're equivalent. Okay? It's just multiple choice. It may or may not be simplified. And if it's not multiple choice, you can't be marked wrong for not simplifying. Who cares? But you've got the calculator anyway, so whatever. So there's the basis of it. The number of ways something can happen over the number of total possible things that could happen. So the range of probabilities is from 0 to 1. You can't get a probability less than 0. A negative probability makes no sense. So 0 means it just is impossible. And a probability of 1 means it must happen. It's like, what's the chance of getting a number when I roll a die? 6 options out of 6 options. 1 is the maximum. 7 on 6 makes no sense. I can't get 6 out of 7 options. 7 out of 6 options. So it goes from 0 to 1. From impossible to an even chance, you'll also hear it just called 50-50, 50% this, 50% that, and certainty. Okay. And again, decimal or percentage, fraction, doesn't matter. Now we start to get into a bit of the guts of it. We're going to head towards playing cards a bit. But no, this also can cause issues to say, oh, I don't play cards. Okay, that's fine. I'll give you a suggestion in a minute, just for a resource sheet aid, just to go, if there's card questions, it's all good. Cards are just a really nice way to explain probability. But we've got an addition rule chucked in here, and that could look a bit foreign. It says the probability of A or B happening is equal to the probability of A happening plus the probability of B happening minus the probability of both of them occurring at the same time. Now, let's explain that with an example, because written like that seems a bit harsh. First example. Okay, it's fairly simple. A multiple of 3 when a die is rolled once. Well, there's only 2 numbers you can roll on a die that's a multiple of 3. 3 itself, and that again could be a technicality. Is 3 a multiple of 3? It is. 1 times 3 is 3, 2 times 3. Even naught would be considered a multiple of 3, but there's no naught. So there's only 2 options. So there's 2 ways I could think of that. I could think the probability of a multiple of 3 is, I could just count them up and say there's only 2 numbers that could happen, satisfy my question. Out of 6 options, question's done. Or I could have said the probability of a multiple of 3 is probability of getting a 3 or a 6. That last formula told me that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of AB. And this formula is totally unnecessary in this example. But just to show, we'll step from this to another example where it matters. The probability of rolling a 3, what's that? 1 in 6. Plus the probability of rolling a 6, that's a 1 out of 6. What's the probability of rolling a 3 and a 6? In one roll? You can't. There's no overlap here, okay? 1 6 plus 1 6 is 2 6, which is 1/3. You think, why would I do it the second way? Yeah, you wouldn't. If you can see the first answer, great. But I'm just leading out that this addition formula will be needed soon. Probably 2 events. We can just add the 2 events together. But sometimes if there's overlap, we've got to subtract it. Let's do one with overlap. Here's one with overlap. And again, you can just do it straight up. Logic will, if you find this stuff logical, you can get rid of all the probability formulas. Okay, any formula I wrote here, if this just feels natural to you, you don't need them. We'll see where you sit. What's the probability of obtaining a number that is even or less than 3 when a die is rolled once? I mean, my gut instinct would be just saying, look, I know I've only got 6 outcomes. Which ones satisfy the question? That is even, 2, 4, 6, or less than 3. Well, that's less than 3. Is 3 less than 3? No, 3 is not less than 3. 3 is equal to 3. So I've got 4 outcomes that satisfy my question. So a probability is just 4 out of 6. I could 2/3 it if I want, don't care. So there's me doing it manually, just picturing the amount of outcomes that satisfy the question. I just want to show that formula, why that formula exists. The formula said probability of A or B equaling the probability of A plus the probability of B minus the probability of AB. In this case, the question is, what's the probability even, or I'll just write it like that with a less than symbol. Okay, it's not a hat and a bum. Probably even or less than 3 is equal to the probability of even plus the probability less than 3 minus the probability of even and less than 3. Because the probability of getting an even number, there are 3 even numbers. 3 on 6. What's the probability of getting a number less than 3? 2 on 6. What's the probability of something that's even and less than 3? 2 satisfied both categories. We've got overlap in this question. We've got 1 out of 6 numbers in overlap. If I just said, my gut instinct is, look, what's the probability of this or that? Just add them. I would have screwed up here, because I would have said, I've got 3 even numbers and 2 numbers that are less than 3. what I didn't take into account was one of my even numbers was less than 3. I've just double counted a number. 2 got counted in this bunch, 2 got counted in this bunch. So that's why the formula says take one of them back off again. 3 plus 2 is 5 minus 1. We get back to 4 on 6. So it's important to show that, yes, sometimes you've got overlap, but you'll be able to work it out yourself. You don't have to do the whole formula. I worked it out myself. I just wrote them all out and ticked the ones that answer the question. I didn't tick 2 twice, okay? I just knew 2 was one of the answers. So, let's check more. And we've got more of these coming with cards. A bag contains 7 red balls, 6 blue balls, 12 white balls. If one ball is taken at random out of the bag, find the probability of getting a white ball. Again, my formula just told me my probability is equal to the number of ways I can get what I want, and there are 12 options, divided by the total number of things that could happen. When I add them up, should I include the 12 white balls in the bottom of the fraction? Yeah. Okay, everything's included in the denominator. So 7 plus 6 is 13, plus 12 is 25. There are a total of 25 balls. Only 12 of them are white. No traps. Okay, I'm only selecting one ball. There's no overlap problem or anything there. Red or blue ball. Is there an overlap in one selection of getting one that's red and blue? No. No overlap issue, well done, Bruce. No overlap. All I need to know is, well, let's just go common sense anyway. These all answer the question. These all answer the question. There are 13 balls that answer the question out of the same amount. Sure, I could have said it was 7 probability of red plus probability of blue minus no overlap. But I prefer just to think 13 of them satisfy my question, 12 of them don't. That's it. Probably red or blue, 13 on 25. Just to check on that, so we've got 25 white balls and 40 black. What's the probability of randomly selecting a black ball? Any? So what I'm testing here is just the trap of a simplified fraction. It could have been very tempting here to go for none of the above. Okay, so this is just a nasty overhead just to say, look, do it manually. Selecting a black ball, there are 40 of them. How many balls are in total? 65. The skill of simplifying a fraction, you can do it manually. We all know we've got the calc now. 40 on 65 equals, and it will show us at that. Basically, I'm saying, how many 5s are in there? There's 8. How many 5s are in there? There's 13. Beware the simplified answer, okay? Because on initial scan, I wanted my answer to have a denominator of 65, but it doesn't mean it's not there. Yep. Okay, so with the cards, again, some of us just won't be familiar. Some of us will be too familiar with them. Now, and there's going to be controversy for card people. I've just gone with a set definition. Half people like it, half the people don't. Numbered cards, I've defined as cards with numbers on them. Hopefully that's not controversial. If a question asks about numbered cards, it's any of these. They've got numbers on them. Picture cards. Who feels uncomfortable with me not including aces in picture cards? Good. Some people call aces picture cards, some people don't. I just tried to get the majority, and I just went for myself with an ace doesn't have a picture on it. Okay? So I'm not calling it a picture card. It's radical, but let's just go with it. Okay, so the technicalities are picture cards are just the ones with the pictures in this set, and aces aren't considered numbered cards, because some people have said before, no, aces are worth 1 and they're worth 11 in blackjack and all that. No, just they're not got a number on it. Let's keep it simple. I don't want to actually try and get good at gambling here. They're just a nice way to ask questions. Stop. No, no jokers. And it's a good question, actually. And let's just lock in that, okay, because also then I was about to just move on and say, I shouldn't assume these things. Clearly half is red, half is black. We've got suits in cards. Each row is a suit. We've got all hearts, and then all diamonds, and then all clubs, and then all spades, okay? So we've got 13 width, and we've got 4 height. 4 13s are 52. So our card questions, there are 52 cards in a standard deck. And the question will say, in a standard deck of 52 cards, or in a standard deck of cards, you may talk about hearts, you may talk about diamonds, clubs, spades, picture cards, number cards, red, black, aces, queens, so on. That's my resource sheet suggestion. Just to note, if you're not familiar with them, just to have a visual aid to check, because some of the questions can get a bit harder than just what's the probability of picking out a red card. Just something like that. It just shows the picture cards, the numbered cards, half red, half black. Nice quick visualization. So when I ask questions here, I'll just pop up the picture of the cards on there. Okay, and yeah. So let's have a look at some questions. I'll just leave that up there. So what's the probability, and I don't care if your answer is simplified or not. What's the probability of pulling out a heart? 1 in 4? You could go that. 1/4 of the pack is hearts. Or you could have said there's 13 hearts out of 52 cards. Again, same answer. 13 on 52 simplified becomes 1 on 4. A king. You could go for the full version, say, well, there's 4 kings on 52. Or you could say there's 1 king out of every 13 in a row. Okay? What's the same answer? Divide top and bottom by 4. It's 1 in 13 or it's 4 in 52. A heart or a king. Is there any risk of overlap? Is it possible to get a card that's a heart and a king? That's why they're nice questions, just to check. Is there overlap? My gut instinct might be to say, well, how many hearts are there? 13. And or, I will say, is a plus. Or is always going to be a plus. But there's that rule just tells us beware of double counting something. How many kings are there? There's 4. So I'm about to make a mistake if that's all I think. Because what do I need to do to that? I just counted the king of hearts twice. Okay? So I need to subtract that overlap. The probability of A plus the probability of B minus the probability of AB. 13 plus 4 is 17, minus 1 is 16 on 52. I said before, allegedly, we didn't have to use that formula. We don't. If you just say, I've got all these hearts, 13, plus 3 more kings, there's my 16. Just don't count the king twice. If it satisfies both questions, just don't count it twice, that's all. So, for me, I'd have the resource sheet to do that. The other trap is, a lot of people will just deal with simplified numbers. Like they might say, what's the probability of getting a heart? 1 in 4 chance. A king is 1 in 13 chance. As long as you do the minus 1 on 52, fine. But if you don't like this stuff, or if you just can picture the pack well, it is safer to count the 16 cards and go, it's not 17, it's 16. All right, Queen of Diamonds, probability of taking out the Queen of Diamonds, 1 in 52. There's only 1 Queen of Diamonds, 1 card out of 52 cards. Yep. A heart and a king. There's only 1 card, which is a heart and a king, and it is called the King of Hearts. So again, it only describes 1 card. We're not at the 2 cards yet. Later, it's like, pick this card and then another one. No, this is 1 card is drawn. A red card, half. You could do 26 on 52 or a half. Yep. Picture card, by definition, a picture. You could look at each suit and say 3 out of every 13 cards. That'll do the job. Or you could say there are 3 by 4, there are 12 picture cards on 52. Same answer. Okay, 12 out of 52 is 3 on 13. Divide top and bottom by 4. Picture card or a spade. Is there overlap? There are picture cards that are spades. So here, let's just do it. What I think is probably the smartest way is me looking at my resource sheet going, picture cards, all of them. Other answers that satisfy it is other spades. Yeah, that would count up all cards that are either picture cards or spades, which would be 12 picture cards, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So that's me doing it fairly manually. Or I could have said, there are 12 picture cards, I know there are 13 spades, but I know that there were 3 cards that were both picture cards and spades. That's 25 minus 3, that's 22 on 52. Same answer, because there were 3 overlap cards. Lathan, nailing it? Loving it? Good. That's cards for the moment. They're coming back, but that's cards for the moment. Hopefully, not too bad. Expectation is a slight extension just to say not just what percent, what probability, but how many times you would expect something to happen. So if I threw one die 500 times, what's the expected number of times that a 6 will be uppermost on the die? In other words, roll a 6. I used to write it that way, and I've been reprimanded. You can't just write roll a 6. You've got to say that a 6 will be uppermost on the die, okay? But I mean, roll a 6. Let me write it. Anyway, what's the probability of getting a 6? 1 in 6. If I do a probability of 1 in 6 500 times, it's a pure multiplication. So yes, you can say it's a formula that comes up soon. E equals NP. Your expected number of something to happen is the number of times you try doing it times its probability. So 500 times a 6 is 83 1/3. Is that a realistic answer if I'm rolling a die 500 times to expect to get a 6 83 1/3 times? A fractional answer doesn't make sense here. What's the most expected? 83. Okay? 83 1/3 is an incorrect answer because I can't roll a third of a die. It doesn't make sense. My answer must be 83. So rounding is important here. 83 1/3 might be a multiple choice answer, and you've got to avoid it to say that doesn't make sense. My answer, my most likely outcome is 83 6s. It's not saying that we promise it'll happen, it's most likely. What's the second most likely thing that might happen? What's the next whole number that's closest to 83 1/3 apart from 83? 84 would be the next closest number. 83 is a third away. 84 is 2/3 away. So your most likely outcome is 83 of them. Your second most likely is 84. So if I spin this spinner and just assume it's all, perfectly split into 4 equal bits, it's all lubricated, all of the, no technicalities, what's the expected number of times it will land on red? Well, I can see you've got a 1 in 4 chance of getting red there. So a quarter times 75 spins, 18 or 19. Which is it closest to? 19, absolutely. The closest whole number to 18.75 is 19. So yes, at the moment it's just a rounding issue. So I'd expect most likely to get 19 times it land on red. 18 will be next in line. This one gets a bit, same question for 90 spins. Probability of a red is a quarter. So 90 times a quarter, 22 1/2, I'm slap bang in the middle. How many times would you expect it to land on red after 90 spins? Gut instinct, maybe. I'm putting words in your mouth. 23 is what maths would say, as in what we've done until now. That when you get 22 1/2, you round it up to 23. Is that in this case? Does the rules of probability follow what mathematicians say? What whole number is closest to 22 1/2? Real life. Sorry? 22 is pretty close. 23 is pretty close. Which one's closer? 22 or 23? Real life, no traps. Neither. What's the most likely event here? 22 or 23? We can't decide. 22 or 23, they're both exactly as likely to happen. It's not just, I'm not just mucking around here. That's the answer. 22.5 is incorrect. 22 is incorrect. 23 is incorrect. The most likely outcome we'll just have to say is equally 22 or 23. So here's a variation. If you land slap bang in the middle with a probability, it means they're both as likely. Okay? If something's 50-50, it's just as likely to happen as to not happen. We don't round it up or anything. You're on the borderline. Both. Okay? If I roll a die 30 times, how many times would I most likely expect to roll a 2? Now, the temptation will be, oh, I've got to do something with a 2 and a 30. That's not really true. What's the probability of rolling a 2? 1 in 6. Okay? Who cares what the number is on the die? You've got a 1 in 6 chance of getting it. So, what's a 6th times 30? In other words, 30 divided by 6. 5. So if I've got 6 equal outcomes, if I do something 30 times, and I expect to get 1, 2, 3, 4, 5, 6, well, if it's a fair die, I would expect to get 5 1s, 5 2s, 5 3s, 5 4s, 5 5, and 5 6s. They're my 30 outcomes if everything comes up evenly. So I would expect to roll a 2. Yeah, 5 times. But the formula we had before said the expected number of times is the number of times you try doing it, times the probability. Yep. Good. So complementary events. The only little bit of notation that comes in is this. But the concept is complementary event is the other thing that might happen. Say that you've got a probability that something will happen, the complementary event is just that it won't. The complement of something is if two people together are meant to make this awesome package, one is meant to be the complement of the other. Okay? That's Ruth. Oh, I've made you sad now. You don't. Oh, sorry. Don't analyse the words. It's not that. Kevin can do that. Okay. So if something's going to happen, the complement is just the opposite. The other, the rest of it. The sum of the probabilities of two complementary events is 1. Well, if something can happen or something can not happen, they add up to 1. There's nowhere else to go. The probability of all events of an outcome adds up to 1. So it's saying the probability of an event happening plus the probability of it not happening is 1. So that's the way to write it. Probability of an event plus the probability of the event not happening. E with a bar on it just means complement of. And just that bit of algebra, subtracting event occurring from both sides, tells me that the probability of an event not occurring is just 1 minus the probability of the event occurring. So you give me a probability of it not occurring, the probability of it occurring is 1 minus that. Okay? The probability of attaining anything but a 3 when a die is thrown. I could do it direct by saying anything but a 3, that's 1, 2, 4, 5, 6. There are 5 out of 6 options. There's my answer. Or I could say, well, the probability of anything but a 3 is 1 minus the probability of getting a 3. Because the opposite of not getting a 3 is getting a 3. Sometimes it just makes life a lot easier. Sometimes you've got heaps and heaps of outcomes. This or this or this and this and this, and we've got all these probabilities. And it might say, what's the probability of this? It'd be quicker to calculate it by saying 1 minus this. Okay? That's why it's there. It's not overly useful yet, but that's why it's there. Like if I just said, we've got a 3 in 20 chance of rain tomorrow, the probability it will not rain must be 17 on 20. It's the amount, 3 on 20 plus something on 20 to give the full number 1. Okay? So the gap between here and here will be the other numerator. Don't have to go there. We've got calcs. But 1 minus that will give you the other probability. So that's going to be a useful tool soon. Another example that's already in the book. We've got a set of cards numbered 1 to 23. One card is selected at random. What's the probability that number on the card is divisible by 5? We've only got the numbers 1 to 23. Divisible by 5 means it's a multiple of 5. It's 5, 10, 15, 20. There's only 4 cards. out of 1 to 23 with those numbers, 5, 10, 15, 20. So I've got a 4 in 23 chance of it being divisible by 5. Here's a very simple example where instead of counting up all the other numbers, 1, 2, 3, 4, skip it, 6, 7, 8, just do 1 minus. Because it's either divisible by 5 or it's not. So the other answer, not divisible by 5, would be quicker to say 1 minus divisible by 5. If 4 of them were, 19 of them weren't. So answer is 19 on 23. Okay? Quick shortcut, but sometimes very worthy. All right, give us more lecture examples. Venn diagrams. It's sad. I still like Venn diagrams. Does anyone hate them? Nobody? Okay, good. Both of those Venn diagrams are as apt as each other. In one of them, it's got raw data, like it's some question talking about letters and where they are. Okay, so these letters satisfy condition A, these letters satisfy condition B. And this is just a summary of them. This is just saying 3 letters are in this crescent, 4 were in here, only 1 was in here, and there were 5 things. Oh yeah, I'll point with that. 5 things out here. Okay. Let's make one. Best way to see Venn diagram in use is just make one. First thing I want to do is make a Venn diagram, okay, from raw data. Most of the times we won't. We'll just get given a Venn diagram, but let's just make one to see where it comes from. A set of cards numbered 1 to 20 is placed in a box with 1 drawn at random. So the one in the book is already done, but let's just see how we do it. The number 1, well, the categories are even numbers or multiples of 5. Is the number 1 either of them? 1's not even, it's not a multiple of 5. So 1 goes out here. Okay, it doesn't satisfy either conditions that we're discussing, even or multiple of 5. Okay, that M is just shortened, multiple of 5. Number 2 is even, but it's not a multiple of 5. So 2 must go here. I wouldn't put 2 here because that would mean it's in both, even and multiple of 5. No. 3 is not even or a multiple of 5, so 3 goes out here. 4 is even, but not a multiple of 5. 5 is a multiple of 5, but it's not even, so 5 goes out here. 6 is even, but not a multiple. 7 is neither. 8 is even, but not a multiple of 5. 9 is neither. 10 is our first one that's both even and a multiple of 5. 10 goes in here. What's the only other one that's going to go in that middle? When we get to 20. 10 and 20 are the only numbers that are even and multiples of 5. The only other one that's going to come in here is 15. So I'll just go through. 11 is out, 12 is even, 13 is out, 14 is even, 15 is a multiple of 5 but not even, 16 is even, 17's out, 18's even, 19's out, and 20's in the overlap. So there's me constructing that. And then in order to answer questions on it, it's just easier to do a summary of it. Just to say, look, there were 8 numbers here, 1, 2, 8. There were 2 in the middle, there were 2 here, and there were 8 out there. And I'll just check that out up to 20, 16, 17, 18, yep, all as well. So that's the Venn diagram. Sometimes you'll just get given that, you may need to construct one. Well, let's determine the probability of the card being an even number. Well, easy enough now. If I'm selecting one card at random out of 20 cards, there's all 20. My numerator, it looks like you could accidentally say there's 8 even numbers, but how many even numbers really? 10. Just because 2 of them multiples of 5, I don't care. I didn't say even number only. I just said how many even numbers are there? There are 10. So the probability is 10 out of 20. In the same way, if I'm asked for a multiple of 5, I don't care if it's even or not. I just want to know how many are in the multiple of 5 circle. There are only 4 numbers that are multiples of 5 out of the 20. The third one says an even number and or a multiple of 5. Well, and or means I don't care whether you're and or whether you're or. You're just all included. In other words, this one is the figure 8. Everything inside here is either even or multiple of 5 or both. So that's a full 8, 9, 10, 11, 12 out of 20. Or I could have said it's 1 minus 8 out of 20. It's 1 minus everything that isn't. Either way, 12 on 20. So, fairly simple one, really. And note the areas of the Venn diagram. So if a question says, what's a probability of A and B? Well, it's only this bit. That's the area that's A and B. A or B, there's controversy here. A or B includes and. If I walked up to someone and said, do you like basketball or tennis? If they liked both, they'd still say yes to me. Do you like basketball or tennis? Yeah, I like both. Okay, so or includes and. If I walked up to someone and said, do you like basketball or tennis only? There'd be no, it's both. So by saying or either basketball or tennis, we go, no, both. So the word either or only means just one or the other. So that's why this was excluded. But if I just ask someone if you're part of A or B, if they're part of both, that's cool. So or includes and, either or only excludes and. Honestly, I reckon that's the worst one of the lecture, the worst confusing bit. But just note that either and or are words that exclude the overlap, exclude the and. Let's do some. This is the most predictable sort of one you'll get. Not like 30 students and here are all their preferences, now take ages forming a Venn diagram. We'll have to form Venn diagrams from stuff like this. Now, it says there are 30 students in an English tute. So in other words, you'll sometimes see this U in a Venn diagram, and all that means is the universal set. That means every question, every option from the question is somewhere in this rectangle. They might be here, 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 or out here, but everything is in there. And here, I'm just going to note, there are 30 students in this tute we're talking about. All my numbers should add up to 30. Of these, 19 study chemistry. I can't just write 19 there, because maybe the 19 are in the C circle, but I don't know, maybe there's 19 and 0, 18 and 1, 17 and 2, I don't know yet. 13 study physics, I don't know where to put them. I can use that. Where can I put that? If 5 study neither subject, they're not in the chemistry circle or the physics circle. Okay? So 5 are out there. But I still need 3 numbers. So, how many students, given that there are 30 in the tute and 5 do neither, what's the total of the numbers that got to fit in this figure 8 thing? They've got up to 25. But my question tells me 19 study chemistry and 13 study physics. What are 19 and 13 add up to? 19, 29, 32. I've got a problem. I've got 32 numbers left to squeeze into this figure 8, but space for only 25. What's that screaming at me? 7 people must be in both. The only reason I could possibly get to a number greater than 25 is if I double count some people. If some people had their hands up for the physics count and hands up for the chemistry count, I'm going to count them twice. I must have counted 7 people twice. The method I'm doing here is just going to work. You just look at how many have I got left to fit in there and how am I trying to squeeze in there. The gap between them must be there. So if I reckon that's true, if I'm meant to have 19 in the chemistry circle and there's 7 there, must be a 12. Because I need a 19 total in physics. Chemistry, sorry. 19 total in chemistry, well 12 and 7 make that 19. I want 13 in the physics circle. What number needs to go here? It better be a 6, because 7 and a 6 make 13. Does that add up right? There are 30 students in English tute. 12 is 19, plus 6 is 25, plus 5 is 30, yep. 19 study chemistry, 12 and 7, yep. 13 study physics, 7 and 6, yep. 5 study neither, 5's out there. Everything is good. So you will always, the question will always have one number that can go straight into the Venn diagram. Sometimes it'll tell you neither. Sometimes, and the easy one to do is when it tells you both. If this question said 7 people study physics and chemistry, I'd put that straight in the middle. Okay? So, and they're a lot quicker. But anyway, if our Venn diagram's right, let's go for it. Find the probability that one student chosen at random studies chemistry and physics. What's wrong with my answer? There's 7 students, but that's not a probability. Sometimes it'll just ask how many, but if it says probability, put it over the total. Physics only, how many people? First question, how many people study physics only? 6. We don't want physics and chemistry. Here's the 6 that study physics only. 6 out of 30. I'm not bothering with the simplifications of them. Don't need to. Chemistry or physics. Does that include the 7 or not include the 7? All was cool. All in with all. Chemistry or physics is the 12 and the 7 is 19 plus the 6 is 25. It's either or the word only, or chemistry or physics, but not both. It might be nicer, but either or only says exclude the centre. The 12 and the 6. All right, 2-minute break there. Oh, okay, I thought you were looking for something. Might switch that off. sometimes. I don't like to read. Well, you could read that or you could play Candy Crush. Okay, another example. Venn diagram stuff. Let's see what this situation is. Now note that our Venn diagrams might have different titles, but they're all going to be two group things. One overall rectangle saying everything goes in here, and there'll be two categories. So initially I already know I can do this. They're very small numbers. A group of 5 students form a band, so I've only got 5 in this whole scenario. All band members, except for the singer, can either play bass or drums or both. Okay, Bill will play bass, Bill will play drums. B, D. So, all band members, except for the singer, can play either bass or drums or both. What does that tell me? A number I can put somewhere. 1 out of them. I mean 4, it means 4 is going in here, but I don't know where yet. But it does say 1 can go out. So there was still a definite. So there's always going to be one number that's definite, either a neither or maybe an overlap. In this case, I took that sentence as saying the singer is neither in the B nor D circles, nor both. 4 can play bass and 3 can play drums. This is heading towards telling me how many can do both. How much room have I got left people that need to go into these 2 circles? 4. How many am I trying to cram in there? 4 can play bass and 3 can play drums. 3 must be double counted. I've only got room for 4 people left. 1 out there, 5 total. So I've only got room for 4. but I've got 7 that claim to be in both circles. So let's see if that works. That the gap between the 7 and 4 is 3. Bass, 4 can play bass, or 3 are there. That must be the other one that adds up to give 4. 3 can play drums. What needs to go here? 0. Because if it's 3 in the drum circle totally, and 3 in the overlap, let's see if that adds up. 1, 3, 1, yep, they add up to 5. 4 bass, yep. 3 drums, yep. Everyone but the singer, yep. It's happened. I reckon that's more of pudding. Chi-Chi, you don't like this one. Was it any particular aspect or just overall? We'll chat later. Okay. It's more of pudding, I think, having small numbers, but I did exactly the same as what I did in the last question. I put the only definite answer in there. I worked out what I had left to put in there and what it was telling me to put in there. The difference between them was the overlap. Now, how many members can play drums only is the question. Well, how many? None. It's asked me for the answer to there. Not probability. How many members can play drums only? None. All 3 that could play drums could play bass as well. Another one. Okay, we've got bigger numbers. What have we got? 40 students, so 40 in total. We've got maths circle, we've got chemistry circle. Okay. So I know I'm fitting 40 in both. Me writing 40 here, by the way, isn't anything official, part of drawing a Venn diagram. I just like doing it to remind myself that's the total. I've got a maths circle and a chemistry circle. 14 are taking maths, I don't know where to put them yet. 29 are taking chemistry, I don't know where to put them yet. 5 students are in both classes. This one's easier, because this one told me the overlap. If 5 are in both classes, this is the first case where they told me the both, not the neither. Now, I don't have to do some big sum here, because if I'm told that, and 14 are taking maths, what must go here? 9. Whatever had to add to the 5 to give me 14 had to go there. 29 are taking chemistry, but there's 5 sitting there. 29 minus 5, that's 24. Am I finished? No, there might be a neither. Let's check. 24 and 5 is 29, plus 9 is 38. It doesn't add up to 40 yet. Must be a 2 out here. So yeah, that up to 14, that up to 29, well, adds up to 40. Everything's Millhouse. So, what's the probability of the randomly chosen, so probability, so I know it's a fraction answer, it's got a denominator, that a randomly chosen student from this group of 40 is taking only the chemistry class. How many? The 24. 5 are taking both, but 24 are in the only chemistry section. 24 out of 40. Don't care about simplification. Yeah? Why didn't I? Just don't care. I could, just not in the mood. If it's multiple choice, the simplified answer might be there. You can't make me simplify it. I just don't want to. Okay. Conditional probability. All right, so the next step with conditional probability is just the way wording is in the question. And it can be hard to pick, well, no, it can be easy to miss, okay. Conditional probability is when, within the question, they tell you something, some information, which you need to answer the question. Like, let's do one. Firstly, it looks like we've got to make another Venn diagram. Fairly standard activity. From a class of 20 music students, all right, 20 in total. 10 play guitar, 10 here somewhere. 14 played piano, 14 here somewhere. 6 played both, good, it's one of them. 6 played both. So to make 10 guitar, 10 minus 6 is 4. To make 14 piano, 14 minus 6 is 8. And to see if there are any neithers, well, that's 18 they all add up to, and the men add up to 20. So, okay, I won't slow down on that, but let's look at the questions. What's the probability of randomly selecting a student from the group of piano players? Conditional probability, this is the bit. I'm only selecting from the group of piano players. The question's asking me to only select from the group of piano players. Up till now it's been, what's the probability of selecting from this group of people? And it would have been out of the all 20. But how many piano players are in my Venn diagram? Not just 8. How many, it didn't say piano only, how many piano players in total? 14. There are 14 piano players, and it's asking me a question when selecting a student from the group of piano players. From these 14 piano players, in other words, out of these 14 students, how many of them also play guitar? Those 6. So consider, cover everything but the circle with the piano circle. There are 14 in total and 6 of them play guitar. 6 out of 14. So conditional probability is when the denominator is not everybody. There is something in the question which is restricting your denominator. And again, I could simplify, but no. If only addressing the group of students who play piano or guitar, okay? What's this? People want to simplify. I'll start simplifying. No, okay. But overall, or you're just being a smartass? Just asking. It doesn't matter whether it's simplified or not, but if it's multiple choice, maybe 3 on 7 is only one there. I do try and make a habit of not caring about the simplification in multiple choice as well, but it might be there. If only addressing the group of students who plays piano or guitar. As in, that's all of this lot, okay? We said piano or guitar was alls and both. There are 18 people who play piano or guitar. That includes both, because there's 2 people excluded. So the denominator here, that's not my answer, that's the denominator. If only addressing the group of students who play piano or guitar, you're only addressing 18 people. How many of them are a piano player? How many of these 18 people are piano players? 14 of them. Yeah. Okay, so there were 18 in the category of people I was talking to, and 14 of those people played piano. Only 4 of them didn't, hence the gap between the 14 and the 18. So you just got to read these questions carefully. We're not done with that. Those questions now are going to make their way into the other things and cards. Given that I picked a heart, what's the probability of? Okay. Given that I picked a black card, what's the probability of? So that's just a contingent question. Conditional question. Now, contingency tables are an option. You can do Venn diagrams or you can do contingency tables. I hate words. But let's have a look at it. It's fairly straightforward stuff. Look at this one here. In a sample of 250 children, 119 have been vaccinated against mumps, 74 got mumps, and 14 were vaccinated against mumps and have contracted mumps. Okay. The data here is started for us. Let's try and make sense of this. Let's fill it in. 14 people got mumps and were vaccinated against it. That's not good, but it happened. So they were vaccinated, but they got it. It's not perfect. 105 people were vaccinated and didn't get mumps. That's more what we expected. 60 people were not vaccinated and got mumps. Well, unprotected. 71 were not vaccinated but didn't get mumps anyway. So there's only 4 numbers in here. But let's add up our totals. 105 and 114 is 119. That's why it said 119 were vaccinated against mumps. 119 people were vaccinated. Fair enough. 60 and 71 is 131. 14 and 60 is 74. Well, that's what it says. 74 contracted mumps, fine. 14 were vaccinated against mumps, fine. 176, and if I add them up, I get 250 as I should. So, in a contingency table, we might have to make it up, we might have to fill it in all ourselves. In this question, all we had to do was do our totals. Notice that this plus this equaled that, and this plus this equaled that. It had to. Okay, so there's only 4 unique numbers, the rest are just totals. Now let's look at that table and answer our questions. If one child is selected at random, it didn't say from a certain group, just one child selected at random. As soon as I read that, it's out of 250. There was no wording in there that said out of only a certain group. What's the probability that child has been vaccinated? How many of these kids got vaccinated? 119. It was a totals question. It didn't ask about whether they got mumps or not. It just said, out of all of these people, how many were vaccinated? Well, 119 out of the 250. And here's a definite situation. Don't even bother with a calc and look for simplifications, just that'll do you. Determine the probability, choosing someone at random, that they did not contract mumps. Out of all of them, how many did not contract mumps? Is it that? Or is it that? That. Yep. Again, we don't care. It didn't say whether they've been vaccinated or not. How many people did not contract mumps? No mumps. 176 people out of 250 did not get mumps. Okay. This one has got a condition in the question. Well, not a condition, it's just a second section. What's the probability they'd been vaccinated and contracted mumps? So they'd been vaccinated and contracted mumps. I'm still selecting out of everyone. What goes on top? So the big fail, they were vaccinated but still got it. 14. Being vaccinated is all of these. Contracted mumps was all of these. 14 people vaccinated and got mumps. 14 out of 250 was that. Not being vaccinated and contracted mumps, well, go to the not vaccinated and still got mumps. Not vaccinated, got mumps, 60. Okay, so it's just slowing down, be careful that you're answering the right question. There's not a trap, it's just 60 people have been not vaccinated and contracted mumps, but it had asked me, what's the probability? Not just number, probability, 60 out of 250. All right, here's one. We're given a selection of numbers. Let's see where those numbers go and fill in the rest of the blanks. A company has a health club available to its employees. Records for last year indicate that of 210 employees, all right, so we've got a total of 210 employees. 90 use the health club at some time. Use health club at some time, 90. Of 170 male employees, there's data. There are 170 male employees. The total of male is 170. Of those 170, 65 use the health club. 65 males use the health club. The rest can come from gaps. Okay? 65 males out of 90, well, the gap plus 5 is 70, 80, 90. It must be 25 to add up to 90. If we've got 170 there and 210 there, it must be a 40 there to add up to it. If I've got 65 plus something gives 170, well, 65 and 105 gives 70. 25 plus 15 gives 40. 105 plus 15 gives 120. 90 plus 120 does give 210. Yep. So notice if in these questions, if you're asked to do one and then you get it all wrong, but you answer the questions with the wrong numbers, it's carried mistakes. Don't just drop the bundle. Carry the errors, doesn't matter. If you do drop the bundle, just fill it with whatever numbers and use those wrong numbers, because you've still got marks for the next bits. So there's my table. If one employee is selected at random, determine the probability the employee is male. What over what? 210 employees, 170 males. Nothing to do with the health club. Okay? 170 out of 210, that's the probability that you've just selected a male. What's the probability that you choose someone at random and that person is female and did not use the health club? Female, did not use the health club. 15, you got 15 people in this whole bunch that you could pick that are female and did not use the health club. 15 out of 210. Very low chance of selecting someone at random who is female and did not use the health club. Okay, so no conditional there. That was just straight up, all normal denominators. Here's conditional. Determine the probability that the person selected was male, given that they use the health club. So what they're telling you is, I pick someone at random. They use the health club. I'm giving you that information, they use the health club. What's my denominator? 90 people use the health club. So given that I chose someone who used the health club, so given that I've got one of 90 people, what's the probability that person was male? 65 out of that 90. You know what I mean? It can be hard to spot, but it said, it gave you information. They use the health club, all right? 65 out of 90. 90 use the health club, 65 were male. Given the probability that a female selected at random used the health club. It doesn't say the word given, but it's telling us I selected a female at random. I selected a female. There's knowledge. Okay? So they've given you some info. It's saying, I picked a female. What's the probability that they use the health club? Out of those 40, 25 females use the health club. Okay? So the probability that a female selected at random used the health club. So I was only selecting from the females at random, 25 out of those 40. So just be careful. It's giving you info. Next. A blood test is used to diagnose tuberculosis, TB. When the results of the blood test are positive, it means that the patient has TB. I wrote that for myself. I wasn't sure. So if a test is positive, you've got TB. When the results of blood tests are negative, you don't have TB. So blood tests are not perfect. What this is saying is this is real life. People who actually have TB, patients who do not have TB. So this means that they had TB and the blood test agreed with them. 6 people, however, had TB. The blood test said they didn't. But here's the truth. They did have it. The blood test was wrong. Okay? So the blood test is not perfect, this test. 14 people did not have TB. The blood test reckoned they did. 126 people did not have TB, and the blood test agreed. You do not have TB. So let's look at our questions from it. How many patients were correctly diagnosed by the test to have TB? Not probability, just what number of patients were correctly diagnosed by the test to have TB? 454 people were correctly diagnosed to have TB. They had it and it agreed. Okay. In what percentage, all right, I'm going to have to convert to a percentage of the blood test for TB were the results of the blood test incorrect? I'm not going to do this manual. How many were incorrect? Which of the numbers in that table were telling the patient the wrong thing? That was the wrong thing. 6 people were told they didn't have it when they did. Any other people lied to? Those 14 people were told they had TB when they didn't. So we want to know when the blood test results are incorrect. 14 incorrect results here and 6 incorrect results here. 20 results out of 600 were incorrect. Okay? Not a perfect blood test. It said what percentage. If I want to convert that to percentage, I get that 20 divided by 600 and I times it by 100 to turn into percent, and it gives me 3.3%. Repeater, I'll just call it 1 DP. So this blood test failed 3.3% of the time, okay? That's not great, but anyway. So there's our, we're into the thick of it. There's our tables, some questions which were conditional, which gave more info. Here's an extension on that, just to check without me interfering. Exactly the same question as the last one. What's the probability that a person selected at random had a positive blood test given that they have TB. None of the answers are simplified, so you can look for your correct denominator that you think. They're asking, the denominators change. We're only talking about people who had TB. And the numerator would be, out of those people, how many got a positive blood test? That sounds right. We're only talking about the TB people. We're only talking about these people. And this many, 454 out of 460 of the people who had TB, 454 got a positive test. Beautiful. Okay, we're on the downward slope. Tree diagrams don't get too vexing. So, consider the tossing of two coins with a tree diagram. First step is, if the question says you've got two coins in your hand and you throw them, or it said you throw one then the other, it doesn't matter. We're still going to pretend we did one then the other. If it said I'm throwing 10 coins in the air, don't do it that way. That would be a horrible tree diagram. Pretend you did it one after the other, okay? The wording will say whether it cares about the order, but the tossing of two coins, totally look at one and then another. Now the first toss could be head or tail, end of story, okay? No other options. So given that maybe head happened, maybe this happened, well, on the second toss, I still could have had a head or tail happen, or I could have had a tail then a head or tail. So there's my entire tree diagram for the tossing of two coins. Now what I can get from that is the outcomes that are potential. I could have gotten two heads, a head then a tail then a head, or a tail then a tail. Note that if it was just two coins chucked up at once, then those two middle ones, head, tail and tail, head, they're the same outcome, a head and a tail. If it was one after the other, then you consider them different. Someone might ask me what's the probability of getting a head then a tail, or a tail then a head. As for the odds of each one, if this was a dodgy coin, I might have a coin that's biased to give heads. And it might have a 0.7 chance of giving a head and 0.3 chance of giving a tail. As long as they add up to 1, that's got potential. If I had one from a joke store. If there's no labels, it's even, okay? This is even. It's a half chance there, it's a half chance there. Every one of these outcomes is just as likely. There are 4 outcomes. They've all got a 1 in 4 chance of happening, okay? No bias, nothing special, just 1 in 4 chance of any of those outcomes. So the probability of getting a head then a tail is 1 in 4. A head then a tail is this one. It's got a 1 in 4 chance. It's got an equal chance as any other outcome. What's the probability of getting a head and a tail? Not then, but and. Means I don't care what order you got them in. Head, tail, tail, head. It's the same answer. I've got a head and a tail. It's a quarter plus a quarter. Or you could say it's 2 out of the 4 equal outcomes. Half of the outcomes. So then the order matters, and the order doesn't matter. Just matters that there's a head on the ground, there's a tail on the ground. If we've got a coin and a die, well, it doesn't matter which order you put it in. Here I've got the die happening first, and there's 6 outcomes. I could get any of those numbers, but I've got to branch off twice on each of those outcomes, because I could have got a head or a tail on any of them. So you can see here, and we'll look more into it next week, that if I've got an option of doing something, there's 6 outcomes here and 2 outcomes here, there are 12 outcomes all up, 6 by 2. And my outcomes are 1 head, 1 tail, 2 head, 2 tail. They're my 12 unique outcomes. And that will, well, that's needed for, what's the probability of getting an even number and a head? If I've got my tree diagram there, I'll just go through and say, well, even number and a head. 2 and a head, not 3 and a head. 4 and a head, not 5 and a head. 6 and a head. Have I missed any? Even number and a head. That's it. The others have tails or odds. So that says only 3 outcomes. And I saw it was 6 by 2. There are 12 unique ones. 3 12s, 1 quarter, same thing. There's my probability. but I really needed that tree diagram to get me there. So, basic tree diagram done. What we need to use now is we've looked at OR along the way. How do we calculate some tree diagram stuff without actually writing it? Before we had the addition rule that said probability of A happening or probability of B was, yeah, add them, but take away any overlap. If it's probability of A and the probability of B, where they're independent events, they don't affect each other, they just times. So probability-wise, OR is a plus, AND is a times. That thing I'll talk to. It's just in the notes. So, here we're going to look at one. A family of 2 children determine the probability of having a boy and a girl. Just to clarify what that was saying about AND is a times, I could label my arms if I wanted. I've got a 1 in 2 probability of boy and a 1 in 2 probability of girl. And all of these are the same things. And I can say the probability of going along having a boy and having a boy is a half times a half. And a half times a half is a quarter. This one is still a half times a half. So that's another way to look at it. Not overly useful here, half and a half, but if I had bias, I'm definitely going to need to know that I've got to multiply the arms. So in that one, it's fairly straightforward anyway. But here, look at this one. A coin is tossed 3 times. List all the possible outcomes, determine the probability of obtaining 2 heads and 1 tail. Actually, we don't even need the product rule in this. We just need 3 coins. We've got head, tail from that head, tail from that head, tail, and then head, tail, head, tail, head, tail, head, tail. I had 2 ways the first outcomes could happen, 2 ways the second, 2 ways the third. 2 by 2 by 2 is 8. The probability of each arm, I could say, is a half times a half times a half, which is an 1/8. Or I could just say, all outcomes, there are 8 outcomes, all equally likely. And what are those outcomes? Head, head, head. Head, head, tail. I'm just following the path that got me here. Head, tail, head got me here. Head, tail, tail. Tail, head, head. Oi. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. Which of them satisfy my question? I've listed all the possible outcomes. That's my sample space. At the end, all the possible things that could happen. What's the probability of obtaining 2 heads and 1 tail? Is that only head, head, tail, or are there others? It didn't say head, then tail. Head, head, tail is clearly an answer. What else? 2 heads and 1 tail. Head, tail, head. That's still 2 heads and 1 tail. Yeah, tail, head, head. But that's it, isn't it? There's no other options that have 2 heads and 1 tail. Yeah? Just the 3? Just the 3. Okay, that's 3 and 8. Okay, so we used our tree diagram to get there. Great. The next one's got a prettier picture of that, I think, just with more questions. 3 coins continued. What's the probability of getting all heads? Well, that's only 1 out of all options. 1 out of 8 options is head, head, head. A tail, then 2 heads? Well, same thing. A tail, then 2 heads is this one. There's no other tail, then 2 heads, because then gave you the order. So 1 in 8. Oh, that's it. It's getting excited. What's the probability of getting 4 heads if I toss a coin 4 times? I don't want to draw the picture. You can see it's getting a bit out of control. We don't need to. You see the pattern that was happening, and once again, we'll talk more about it next week. Probably getting 4 heads if I toss a coin 4 times. When it was 3 coins, it was 2 outcomes by 2 outcomes by 2 outcomes. Tossing it 4 times, 2 by 2 is 4 by 2 is 8. There are 16 outcomes. How many of those outcomes do you reckon is 4 heads? Just the 1. Okay? Just picture the last one. On one side you got all heads, one side you got all tails, and all sorts of combos in between. We don't need to draw the picture. It's just to look at the trend. 4 heads would be 1 in 16. What would 5 heads be? Tossing 5 coins. It'll be a 1 in 32. Okay? Okay. Similar question. No tree diagram. Definitely not. What's the probability of randomly guessing all answers correctly for the 8 multiple choice questions in one of our quizzes? So ignore the written. We know you got a 1 in 4 chance of guessing each time. And they could all look okay-ish. Which one's the truth? It is B. Because what's the probability of getting question 1 right? 1 in 4. And getting question 2 right? 1 in 4. And getting question 3 right? 8 times. And the quick way of writing a quarter times itself 8 times is a quarter to the 8. Okay? That was just lining up 8 of them and timesing. Sweet. Or next week. This is where the multiplication comes in. Outcomes with unequal probabilities. So there's some bias. This is not a fair coin. I need to label these tree diagram arms. I choose 2 marbles at random from a bag containing 5 blue marbles and 3 yellow. So 5 blue, 1, 2, 3, 4, 5, and 3 yellow. Find the probability of choosing 2 blue marbles if I replace the first marble before selecting the second marble. Well, first marble, we walk into a bag that looks like this. There are 5 blues and 3 yellows. So the probability of getting a blue marble is 5 out of the total 8 marbles. The probability of getting yellow is 3 out of the 8. Yes, they add up to 1. 5 eighths and 3 eighths is 1. They've got to add up to 1. Okay? There's no other option. Since I do replace the first marble, so I take it out, look at it and put it back, when I go to select the second marble, I've got the same bag. It's different if I left it out, but I didn't. It's still a 5 in 8 chance of getting a blue, still a 3 in 8 of a yellow, still a 5 in 8 blue, 3 in 8 yellow. So if I want to work out the probabilities of each outcome, it's not just 1 in 4, 1 in 4, 1 in 4, 1 in 4, because it's biased. 5 eighths times 5 eighths, I'm just going to cheat with and say to multiply 2 fractions. Multiply the tops, 5 by 5 is 25. Multiply the bottoms, 8 by 8 is 64. So it's 25 in 64 chance of getting 2 blues. A blue then a yellow, well, it's a 5 by 3 on top and an 8 by 8 on the bottom. Here is a 3 by 5 on top, which is still a 15, on an 8 by 8 on the bottom. And here's a 3 by 3 on the top, on an 8 by 8 at the bottom. Notice that the numerators, 25 plus 15 plus 15 plus 9, add up to 64. So all of the outcomes add up to 64. It's just a bit messier than before. So now we can answer the question, find the probability of choosing 2 blue marbles is 25 out of 64. If they ask me what's the probability of getting a blue and a yellow at the end, I'd say 15 on 64 plus 15 on 64 is 30 on 64. 2 yellows is 9 on 64. So there's us labelling our arms if we put the first marble back in. I've got to imagine the second question straight up would be, oh, I had the pretty version. If I do not replace. Okay, exact same question. Clearly, the first thing's the same. Is the question the same? Yep. I had 5 out of 8 blue and 3 out of 8 yellow. Now let's imagine if I walk along this arm, that happened. I got a blue marble. So the bag I'm selecting from then has how many blue marbles in it? Only 4. Because I picked one and I did not replace it. How many yellows? All 3 yellows are still in there. So what's the chance when selecting from here of getting another blue? 4 out of only 7 now. So if I don't put it back in, we lose a marble each time we go. I'd then be 3 on 6, 2 on 5, so on, if I kept trying to do that. But since I had 5 blue marbles out of 8, and I took a blue marble out, that's what it says, I've only got 4 out of 7. What's the probability of getting yellow? How many yellows are still in the bag? All 3 are still in the bag. And hopefully that makes sense, because 4 sevenths and 3 sevenths add up to 1. All little sets of arms. Sometimes there might be 3 outcomes, 4. They've got to add up to 1. Without me drawing a picture, let's do this one next. I had 3 yellow marbles out of 8. I did pick a yellow marble. What's the chance of getting another yellow marble? Only 2 in the bag. Only 7 left. What's the chance after picking a yellow of getting a blue? All 5 are still in the bag. Do 5 sevens and 2 sevens make 1? Yep. So just a bit of a self-check there. They must add up to 1. So firstly, denominators are always the same. If it went from 8 balls to 7 balls, all 8 denominators, all 7. I had 5 blue balls, went down to 4. I had 3 yellows, went down to 2. And the other still add up right. And then what was the question? Well, the probability of choosing 2 blue marbles. It just wants to know the probability of coming along this line. The probability is doing the 5 by 4 as 20 and the 8 by 7 is 56. So the denominator is not 64 this time, it's not 8 by 8, it's 8 by 7. And the numerator reduced too. So I've got a 20 in 56 chance. Yep. Another. At least 1, at least and at most. We'll use common sense to analyse it, but here's where we're going to use this complementary event thing. We'll explain that in terms of an example. What that little equation thing was saying, if I'm tossing 3 coins, what's the probability of getting at least 1 head? What's the opposite of getting at least 1 head? I mean, at least 1 head, has that got yeah, that's got at least 1 head. That's got, I'll start from this end. That's got no heads. That's got at least 1, at least 1. Is 2 at least 1? Yeah, at least 1 means, at least 1. How do you, at least 1 means you've got 1 at least. I'm just rearranging the words. That's got a head, that's got 2, that's fine, that's got 2, that's got 3. I could work them all out. What's quicker? 1 minus that. So this is just saying that if I'm asked what's the probability of at least 1 head, that's equal to 1 minus the probability of no heads. Okay? And the probability of tail is 1/8. 1 out of 8. So it's 1 minus 1/8, which is 7/8. I know I could have added up all of them. But if this was biased probability, that would have taken me ages to add up all of them. Don't want to do it. I want to do 1 minus the other one. So let's check one where it's... Here we go, biased. This is where it would be horrible. Tossing 3 biased coins. What's the probability of getting at least 1 head? Okay, same question. At least 1 head is all of these. So I want to do the probability is equal to 1 minus the probability of 3 tails. So I only have to calculate 1 set of arms here. Now what's the bias? These bias coins land on heads twice as often as they land on tails. So what's the probability of getting a head? If you're twice as likely to get heads than tails, it's like for every 1 head, for every 1 tail you get 2 heads. So what's the probability? Heads is 2 out of 3. Okay? For every 1/3 of the time you'll get a tail, 2/3 you'll get heads. So I just think of that saying if it's twice as often, then it's 1 head, 2 tails. Oh, sorry, 1 tail, 2 heads. So heads is twice as often. I've got a 2 in 3 chance of getting heads. What's my chance of tail? Only 1 in 3. 1 in 3. 1 in 3. What's the probability of getting 3 tails? It's a 1 by 1 by 1 on the top. 3 by 3 is 9 by 3 is 27 on the bottom. Much, much quicker than working them all out. 2/3 times 2/3 and 2/3 with some 1/3 in it. It's just 1 minus the event that does not answer your question. And in this case, yeah, a third by a third by a third. Remember not to just add them or anything, or just go to the calc. But 1 minus a 27th is 26 on 27. Good. Okay. When tossing back to 3 fair coins, what's the probability of getting, and now here's at most. Just want to tick off what means at most. We just said at least and we understood it. At most 1 tail. Does 3 heads satisfy that question of getting at most 1 tail? That means getting at most 1 tail means I'm setting my maximum at 1 tail. Does 3 heads exceed my maximum? Actually, it doesn't. What about 3 tails? Does that satisfy at most 1 tail? No, that's not. At most 1 tail. 2 is too many. At most 1 tail. 2 is too many. 1? At most 1. I'll accept 1 tail. I won't accept 2 tails. I'll accept 1 tail. I'll accept 1 tail. 3 heads. Is it at most 1 tail? But am I just wording the question wrong? Everyone's giving me the... Someone go like that. Thanks, Tommy. Exactly. Maybe I just worded the question wrong. At most 1 tail means I want 1 tail maximum. I don't care if you give me none. But at most means don't give me more than 1 tail. 3 heads is fine. At most 1 tail means I don't want more than 1. Give me anything less, fine. Give me no tails. Give me 1 tail. Don't give me 2 or 3. So at most, just think of it as in, that's my maximum, and anything under this maximum is fine by me. So, 1, 2, 3, 4 out of my 8 options. 4 out of 8 is 1 in 2. Because I'm back to the fair coin here, okay? This was just an analysis of that term, and you can see, yeah, it's confusing. At most means I'll accept that and anything less, and nothing is less than having 1 tail. Okay, the very last run is just cards with 2. So, and it's without replacement, so the denominator is going to drop. We're only going to take 2 cards, but if I've got 52 cards in the first lot, after I've taken 1, I've only got 51. And I'm going to do all of this unsimplified. It's just much easier. If I take 2 cards out of a pack, what's the probability the first card I pick is black? It's half, but I'm going to do them unsimplified. Would you agree 26 out of 52 cards are black? And I didn't put it back in. What's the chance now of picking out a black card? There's only 25 black cards left in the pack now, because we took 1 out. How many total cards? Done. I won't bother multiplying them out. Yes, I could stick it in the calc. The important thing is how we're getting the answers. The cards are different colours. For the cards to be different colours, what must the first card be that I pick? Right? Totally. What's the probability of selecting a card that's red or black? Red or black? No, what's the probability of picking a card that's any colour at all? I don't care what happens on the first event, okay? Because, I'll word it this way. Same thing. I've got 52 cards, I don't care which of the 52 I pick. Don't care. Same as just writing 1. But given that I picked a certain colour, what's the probability now of picking the other colour? Pretend you picked a red. What's the probability of picking a black now? There's still 26 red cards in there because I didn't pick out a black, but there's 1 missing from the denominator. The numerator did not reduce, so it doesn't matter which one you pretend you got. Whatever colour I got, there are still 26 of the other colour left out of only 51 cards. Ish. Both cards are spades. What's the chance of the first card being a spade? You could go 1 in 4, or I'm just going to keep unsimplified. 13 out of 52 cards are spades. What about the next card being a spade? 12. Only 12 spades left, only 51 cards left. Great. Both cards are the same suit. What suit must I start with? Who cares? If they're going to be the same suit, who cares what the first one is? We just then want the same. So I don't care what the first card is I pick. Pick any card. Now pretend you picked a heart. What's the probability of getting another heart? They're worth 13. There's only 12 hearts left. So whatever suit I picked, there's only 12 remaining of that same suit. So for it to be the same, I picked one, I don't care what. There's only 12 of that suit left because there was only 13 to start with. How many more have I got? Like 3 or 2? Okay. A spade, then a club. What's the probability of getting a spade? Or how many spades in the pack? 13 spades out of 52 cards. How many clubs now left in the pack? Still 13. But there's 51 cards. No big trap there. Cards are of different suits. What must I pick out first? Anything? Now pretend you picked out whatever suit you want. Spades, club, diamonds, hearts. How many cards of a different suit are left in the pack? Say I picked out a heart. I picked out one of 13 hearts. How many non-hearts? 3 13s. There's 13 non-hearts, 13 non-hearts, there are 39 non-hearts left in the pack. Out of, cool, 51. C cards are fun. All right, sweet, cheers. So you'll get an average of all of your marks, and your 20 unit will count twice as much in that average. So you'd like get all your 4 Sem1 marks, or 4 of them, and you've got 3 Sem2 marks, but count it double, your 20 double, so it's like there's 8 marks. Add them all up, divide by 8. We'll give you your average from Easter. Say your average from Easter, say you scrape 50% average. Your ATAR, we've got a calculator here that calculates, it will come out at 69. If a 60 ATAR comes out about 75-ish. Sorry, a 60 average marks comes out about 75-ish. I can send you the calculator if you want. They're going to distribute it later, but we really...
Yeah, no, because I'm like, I got 61 and then I'm averaging like 70, 80.
Okay, well you can put guesses in there for the others that don't know yet. And see what will happen with that. So... Yeah. So you've got Excel, whatever you've got Excel. Yep, okay. Good. That's all right, I need this. Yep, okay, cool. Done.